We talked about CBRS from a technology perspective. Let's bring it a little bit more practical and let's talk about network planning for CBRS. So how do you do it? What tools do you use? What's that look like? So from a, what process do you need to go through? It's going to look very similar to Wi-Fi, actually. You're going to have your wireless coverage and capacity planning. You still need to do some planning up front to understand how much capacity, what your coverage area looks like, and how many radios you're going to need. You need to start thinking about, especially early days of this market, what devices you're going to use and how you're going to do authentication and SIM provisioning. And then you need to think about enterprise network integration requirements, since more than likely, if you're deploying this private LTE, it's going to overlay to your enterprise network. You need to think about cabling, switching, routing, firewall integration, all your usual stuff that you need to integrate with because it's not handled for you. It's not a separate segmented system. So what do we need to do for coverage and capacity planning? What are the important and critical factors? You need to know the location of the network, since, again, we talked about SAS quite heavily, and the requirements for that are geolocation. You need to know exactly where radios are being deployed. So the design is going to be different, not only because of the facility characteristics that you're used to, but also based on the very specific geolocation of the network deployment. You need to know what spectrum is available at that location, and you're going to base your planning around that. You need to know the facility type and the coverage area that you need to serve. So you need to understand what your use cases are, how much area you need to cover for those business processes or use cases. And then finally, all your capacity requirements of number of devices, what applications are they running, and how much bandwidth they need. And when we get into LTE, some of the interesting things are you might actually want to know more than just the bandwidth requirements of the applications. You might want to know its latency sensitivity. What are its thresholds for packet error rate before the application starts experiencing problems? Because a lot of the targeted use cases are very mission critical use cases where applications have very well-defined or tolerances for packet error rate and latency. We can start to get into robotics, automation, things of that nature with mobile edge computing platforms and things like that. And we get into very strict application requirements that you need to meet. So I'm going to talk a little bit about the first step in this process, which is the network planning as far as a rough order of magnitude of what spectrum do I have available and how many radios do I need for my use case. Celona has a network planner that is out there free to use. Going to have you log into that here tomorrow, actually, and start using it. But I'm going to give you the URL, and you can feel free to go in and play with it ahead of time. It has some core functionality that you should be aware of. You're going to put in a specific address or geolocation, and you'll understand it'll do a real-time spectrum inquiry for that specific location. So you know from the SAS vendors, being Federated and Google, which is the ones we're using right now, what spectrum is available in that specific location. That's a real-time lookup that network planner is going to do for you. You can put in square footage, or you can draw on a map the outdoor area, if it's an outdoor coverage model. How large of an area are you looking to cover? It does the SAS inquiry, and you can also do what-if analysis modeling. So again, earlier I mentioned if you're realistic versus more conservative or worst case use cases for how much spectrum you might have available. 150 best case, 110 we're thinking is more realistic for most environments. 80 megahertz available if you're in a PAL area where it's been fully deployed. 70 megahertz if all the PAL's been deployed and you're in an incumbent area. You can do some what-if analysis modeling of the SAS says I have 150 today. What if I'm planning for 3 years down the road and all the PALs are deployed? Maybe I want to model that for a more conservative 80 megahertz down the road, and I don't want to redesign later. You can model that in our network planner and say, okay, SAS told me 150 is available. What if I change it down to 80 megahertz? How does that change the equation? What's my model look like then? And then you should know on the back end, this isn't just simple math, based on spreadsheets or tables or something like that. We're doing sophisticated modeling on the back end that is actually discrete event network simulation and regression modeling. So we've done a lot of regression modeling for a lot of different facility types based on large data sets of hey, what does office environments look like? What do warehouse environments look like? What do shipping ports look like? So we've got a number of different regression models that have large data sets underpinning them that we do this regression modeling on. So you'll select a facility type, and that'll determine the RF path loss modeling that we do. That'll determine the topology, like height variation in the environment. We'll do RF link modeling. And based on how many clients you put in, we'll actually model them spread out throughout the coverage area that you've defined. And each one will get mapped to, for instance, what's the RSRP at that location, potentially, what's the SINR that they can achieve. And then with LTE, there's very defined mappings between SINR and data rates, which is actually tested and validated on most or almost all LTE chipsets by the carriers to make sure they meet performance standards. So there's very well-defined mapping in LTE between SINR and data rate that's achievable, and it's tested and validated to those thresholds. Correct, the chipsets actually measure, yep. So this is what the network planner looks like on the web page. Feel free to go hit this web page on a device if you want to and start playing with it. The only requirement is there's no login. You just have to submit your email to use it. So we won't spam you, we promise. You'll get once a month, I think potentially a Celona newsletter in your inbox just saying, hey, here's what we're up to. And you won't get anything more frequently than that. So go ahead, feel free to start playing with it if you want. And we'll do some you'll get some hands-on time with it tomorrow. We'll actually run through some example scenarios in the hands-on section and have you model a couple of different environments, both indoor and outdoor. But there you can see where you put in an address. On the right-hand side, it'll look up the spectrum and tell you what's available there. That's all interactive. You can check on the different green check marks to uncheck them and see, well, what if I have less spectrum once the PALs are deployed or something like that. You select a facility type from the drop-down menu, and if it's indoor, you can do square footage. If it's outdoor, you can do square footage estimate, or you can actually draw a zone on a map like I have here. Draw it on a map, and it'll actually compute the square footage for you. And you've also tied it to a geolocation, obviously. And then below that, what I'm not showing is there's some capacity planning of number of devices and their bandwidth requirements, both uplink and downlink, so we can properly model that. The uplink versus downlink bandwidth is important to model correctly because LTE is a scheduled protocol. So the whole channel isn't taken for uplink or downlink on a burstable fashion like Wi-Fi. It's scheduled transmissions, and there's a weighting algorithm in the scheduler that says I want 60% downlink, 40% uplink, and you'll have some control over that in a network deployment. We'll get into that a little bit later on the LTE stuff. It's called a LTE frame configuration profile. So the other thing to note is that the eNode B, that's the terminology for a radio. The number of radios scale with the available spectrum, but it's not a one-to-one linear relationship. It takes into account the capacity requirements and the modeling done on the back end on the system, as well as then the LTE interference, intercell interference coordination. It's a very technical term in LTE on how it handles interference. So with Wi-Fi, if you're familiar with co-channel interference, preamble detection and backoff, LTE IC-IC is kind of the terminology they use, and that is essentially the high-level view is that's where each one of them can transmit simultaneously, and they just have a SINR impact to one another, potentially dropping the data rate depending on how high that SINR interference is. So a lot more frequency reuse in LTE is capable, and we model that in the system as well. So what you'll see here is when we have a given capacity requirement for a use case, and then we start taking away spectrum, initially you might not even see your radio requirements increase, because we can do the frequency reuse over that area and still avoid interference. Once we start having an SINR impact, you're going to have potentially lower MCS data rates for clients, and then you're going to have to start increasing your eNode B count to increase the capacity to meet those requirements again. There's a question? So the question is IC-IC limited to the eNode B, or does the client take advantage of that? LTE is a scheduled protocol. The eNode B, or the radio, controls both uplink and downlink transmission, and they control it completely. So the client, a lot of things are different than Wi-Fi. You don't need clients to implement things because it's controlled by the infrastructure. So kind of a different mindset to start getting into for a lot of these topics is just understanding that the eNode B or the infrastructure can actually control a lot of this without clients having to do anything.
eNode B is industry generic term, or is it yours?
eNode B is an industry generic term for LTE. It's called Evolved Node B. I'm going to get into terminology when we get to the LTE section. I'll have a page for you that goes through some of the terminology and kind of what they mean. eNode B, just think of it as a radio, an infrastructure radio. And again, how much spectrum should you plan for? We've covered that already. So here's an example. If I have a 10 million square foot outdoor environment and I'm modeling a very specific capacity requirement, right? So this is a capacity-driven model. I'm having enough radios that are being driven by capacity that I could actually, if it was coverage, I'd need less. So I'm just saying I've put in enough capacity that, I've got increased density in radios to serve this capacity. What happens if I start taking away spectrum? So let's say, I started with 150 megahertz spectrum, and then I start saying, nah. I start going down, and I say, realistic is 110. I go from 150 radios required, 150 radios required to 155. And I've taken away 40 megahertz of spectrum. I've taken away almost a third of my spectrum, and I've only gone from 150 to 155 as far as infrastructure radios go. Again, because it's non-blocking interference, so I get better frequency reuse out of the system. More conservative use cases, if all the PALs are taken or if you're in a DPA area with incumbents, again, you start to have that hockey stick effect once you get down to really low numbers of spectrum because the frequency reuse just gets really, really tough to match for. But for most use cases where you're even conservatively planning for all PALs to be taken, there's not a huge impact into the number of radios you need to plan for. Potentially, 9% more radios, 10% more radios than you would otherwise plan for. So even if you want to be conservative, it's potentially you're talking about, customers and their budgeting and their worst case scenario. How much do I need to budget for? Well, let's go ahead and budget if all the PALs are taken, even though none of them are taken today, and I just need to increase my eNode B count by like 10%. It's not dramatic. So just to give you a flavor of, what the planner takes into account as far as LTE frequency reuse and how that modeling is impacted. Don't expect you to understand, the depth of that, but just understand it's not dramatic.
Is there a negative impact from over-deploying radios, like you do with Wi-Fi, where you get less?
So the question is there a negative impact to over-deploying radios? I think you're getting at like management overhead just for beaconing and things like that. And so LTE as well is different. It has defined subcarriers and tones for control channel information that does not grow. It's not dynamic. So you can, as long as you don't have a capacity from a client perspective, density requirement that's killing your network, you can deploy as many LTE eNode Bs or radios as you want. It's not going to impact your capacity because even if clients connect to all of those radios, again, they're all kind of synced up and they can avoid that interference as long as you're not saturated already. But it'd just be a waste of money from deploying infrastructure perspective. So what tools can you use? Well, CBRS is very new spectrum. There's not a lot of tools on the market to design for this. Celona as a company is partnering with IBWave. IBWave is essentially the standard for indoor cellular design and planning. They have support for the CBRS band already. They're adding to their component and parts database for specific radios and antennas as we speak. So you can do a predictive design and an RF site survey in IBWave today. And we'll step you through some of the tools and capabilities of it. The IBWave team is here this week, so if you want to go talk to them, I would recommend that. Jamel is around, and you can go talk to him and get more details on their solution. But this is a good tool right now. It may not be in your suite today, but if you're looking for designing for both Wi-Fi and CBRS moving forward, it has capabilities for both. They do 3D modeling. So this is a 3D model actually of this conference center. They've done this for the WLPC conference in years past as well. They've 3D modeled Wi-Fi in the environment. We worked with them to 3D model and plan for CBRS in the conference center. So here, they can work up a 3D model of the environment. You can see this is the RSRP, which is analogous to RSSI in Wi-Fi world, the signal strength at different, throughout the environment. So RSRP is receive signal, receive power. Essentially, it's a dBm value for signal strength. Just like you think of it as RSSI you do today with Wi-Fi, even though RSSI used to mean, and by the standard means a scale of 0 to 100, we use it as dBm in Wi-Fi today. That's what RSRP technically is. So technically, we're not using RSSI the way it was defined. We've adapted it to analogous to what RSRP is in the cellular world. So it's just receive power. And you can see here, this is the model of the conference center. We have 2 eNode Bs as the circles on the map there. One is in the back corner of this room, which is the one on the left-hand side of the map. The other one is out by the lobby, which is the one on the right-hand side. And you can see the signal propagation through the environment. And this is predictive model, so this is not actual measurement. This is, we put in the blueprint, we've put in the walls, we 3D modeled it, and then this is what put in the transmit power, the antenna, gain and directionality and all that, and this is what the model says should be the coverage in those areas. So all of that capability there. The other thing to think about, and I'll touch on very briefly, is that when you're designing for cellular, you need to design for different RSRP values than you do for Wi-Fi. So in Wi-Fi, it's typical to design for, let's say, a neg 65 dBm everywhere. In cellular, that's more like a neg 90 dBm everywhere. Because our receive sensitivity at the resource block level in OFDMA, we can actually maintain a connection all the way down to neg 120 or neg 125 dBm. So for us to design, we're designing to about a neg 90 threshold typically, rather than a neg 65 threshold. So you'll see that reflected in the lower end limit. So the lower end, if you can read it down here, is neg 120 dBm. That's kind of where the cutoff is from the visual. Yeah. It's a 15 kilohertz subcarrier. I'd have to do an online calculator to look at what the noise floor is. Somebody want to pull one up? 15 kilohertz is much lower than a 20 megahertz channel. So like 20 megahertz is neg 101 dBm, right? 15 kilohertz for the smallest, well, actually the smallest resource block is bigger than 15. That's the subcarrier. I'd have to look it up. Oh, you're talking kilohertz though for potential. It's all based on the resource block sizing. So with the smallest resource block, I mean, it would go really low. I'd have to go look it up. I have some LTE information on the subcarriers and the resource blocks, and we can plug that into an online tool and see what the noise floor would be. But again, here, we're talking the next one, SINR. This is a little different than signal-to-noise ratio in Wi-Fi as well. Same concept, but we're taking interference into account. And remember how we talked about LTE's frequency reuse and intercell interference coordination, ICIC? We're taking into account interference from my other radios, raising my interference in SINR. So this takes into account the SINR from all my radios in my own network, not just the SNR from the noise floor given the channel bandwidth. So it's a little bit different because Wi-Fi, we're always talking about SNR, just the channel, the ambient noise floor. Here we're taking into account the interference from our own radios as well. So question was, what's this eNode B in the conference? What is it? It's ERRP. I believe it's 24 dBm output and a 6 dBm gain or dBi gain antenna. So it's around 30 dBi, I believe. Yeah, and just rule of thumb. I mean, I hate rule of thumb, but you're going to see larger coverage area off of a CBRS radio at a comparable power level than Wi-Fi, just because of the lower receive sensitivity. You can get a lot farther away from this unit and still maintain a connection. And that connection can still be fairly robust as well. The smallest resource block, I can still get through, a couple usually a megabit or two download still. Whereas Wi-Fi, your lowest data rate's in 5 gigahertz, like 6 megabits per second. I can actually go down to a lowest data rate in LTE, much lower kilobits per second if I needed to. And the other interesting thing about LTE from a planning and design perspective is that there's very well-defined SINR to MCS or data rate mappings for LTE. And these are tested and certified and validated before a carrier will actually put them on their macro network. So at this SINR, you need to achieve this performance level. And every client device is validated before carriers will put it on their network in that fashion. So by using CBRS and LTE, the enterprise network kind of gains because of the work the carriers do. So given a given SINR, you know to a fairly good degree of certainty what data rate a client's actually going to achieve, and you can plan for that. There's not quite the wide range of variability in performance on the client side like you see on the client side in LTE like you potentially do on the Wi-Fi side. So again, it's just differences, right? So if I know the SINR from this previous planning, I can understand exactly what MCS and data rate my clients are going to get and what performance they can achieve.
How do the transmission data rates map out to actual application throughput?
Yeah, so the question is, how do the data rates map to actual end user application throughput? Yeah, that's a much more complicated conversation, quite frankly. I think we'll probably have to take that one offline. That gets into all the low-level details of LTE and how, what's overhead and what's control channel, and also the scheduler of like what client density you have and what the demand is. Because the QoS scheduler through priority can weight which clients through the EPS bearers, which is the QoS functionality in LTE, which clients get prioritized better than or higher than others. So it's not a simple answer, I would say. And everything that you're going to Google out there, and if you Google this, you're going to find all the macro carrier estimates, which again are assuming, macro networks that have hundreds or thousands of clients on them. And I even have one in LTE on a slide up here of, if you're getting 600 megabits data rate and your average download is 60 megabits, you think, well, that's horrible. I'm only getting 1/10, but you're sharing it with everybody else. So again, you got to temper what you Google for in LTE because you're going to get a lot of macro data that is more just what could I get as an average public consumer. The private side will be different. So after you've done your predictive planning, you need to plan to integrate with your network. So that means from both the radio, the Celona Edge, which is the packet core functionality, and then the management or the orchestration layer, what touch points do you need to think about of integration into an enterprise network? So from the RAN side, you need to touch network infrastructure for cabling, what VLAN segment devices are going to go into, IP addressing, all of that. You need to touch into your security infrastructure. Tunnels are created between the radio and the packet core. We'll get into the LTE section what protocols are used, but if you're going across a routed network that has any security, you need to make sure you open up certain protocols for the radio to talk back to the packet core. The packet core, the Celona Edge, or what we call the Edge, you're going to talk about end user authentication, how you map SIMs to users, what traffic controls you have, what QoS policies you have for different groups and applications. From the orchestration perspective, you might want to tie in with the identity management to map SIMs to users in your directory structure and derive policy off of that. You can also potentially integrate with Radius servers as well in order to authenticate through the SIM, but then authorize what policy and access they have through a Radius system still. So you can actually bifurcate and say authentication is in the SIM infrastructure, authorization of what they have access to, then I look them up in Radius and map them or something like that. So again, potentially a lot of integration points depending on what that enterprise environment looks like. Just know it's just like Wi-Fi, a little. As far as integration, it's just a little bit different.
Is open authentication an option where you don't necessarily have to register?
So the question is open authentication an option? The answer is no. Everything has to have a SIM. It has to authenticate. By default, that would be SIM AKA. There are other like USIM technologies that can use EAP authentication and certificates and all that. So you do have a choice, but there's no concept of open or pre-shared key in cellular. So again, talk difference in use cases. You're going to have use cases for Wi-Fi that cellular can't handle, like just open networks. With Celona, we do zero-touch provisioning. So essentially, our systems call back out to the orchestration layer. You don't have to put an IP on systems. You don't have to do anything other than make sure your infrastructure can allow them to call back to the orchestration layer, get provision, download their policy, and start operating. So really, it's really simplified compared to a carrier network. You're not manually configuring and integrating a large number of components. You've got a end-to-end solution where you can deploy a packet core, and you can deploy radios. They'll automatically register with their assigned packet core as long as you've defined the policy in the orchestration layer of this radio is at this site handled by this core. We'll get into some more specifics of that tomorrow when we go through the Celona solution. But just understand from a market perspective, the goal is to streamline the deployment so people don't have to be cellular experts to deploy the systems. Just like people don't have to be Wi-Fi experts to deploy Wi-Fi today, these solutions are completely different than how the carriers approach them. And so they have different business requirements that we need to meet. From a RAN deployment perspective, again, you can break it out. If not everybody doing a radio install has to be a CPI. You can have any company that you contract with go hang an AP, go install an AP, as long as you have somebody in the authority chain, whether that be the customer, a partner, a managed service provider, that is taking responsibility for that outdoor AP or high power AP and certifying that it was installed in the correct location with the correct power and all that.
Are we going to see carriers trying to use CBRS for picocells like they do today for other bands?
So the question is, are we going to see carriers try to use CBRS for picocells and other stuff? I think once carriers start rolling out 5G, they're going to be doing some county-based PAL licenses for 5G for outdoor coverage areas. Penetration, like indoors from carriers, I don't think is going to happen very much. They're going to go after very large venues, like stadiums and stuff, probably, potentially. But they're not going to be, I doubt they'll be able to penetrate into any other locations besides those.
I mean, we'll ship you a picocell, you plug it in.
Oh, you mean like order your own?
Fill it in a cover.
Oh, so the question is more like a femtocell type deployment.
Yeah, am I going to have employees of my institution show up with one that they're supposed to use at home?
Yeah, I can't really say what the carrier's business model is. I mean, they've kind of moved away from femtocells from a large, perspective. I wouldn't anticipate that to be a huge thing, but again, that's something I probably can't predict.
A requirement is to pretty much be always online, always have activity because you have to go and check in periodically, go through those elements. Is there any other thinking any use cases where it's more an offline or partial?
So the question is, since it has to be online all the time to maintain the grant, the spectrum grant from the SAS, is there an offline mode or perspective? Right now, the offline mode is just for stability reasons, that you have a grace period before you have to stop operating. It's meant to be pretty much always on though, always connected to the SAS.
Cruise ship is not going to benefit from having CBRS radios on the ship.
Well, a cruise ship goes outside of U.S. territory, so.
Well, I mean, because that's the gray area already with.
Yeah.
Which is great to put a ship on.
Yeah, that question I can't answer. It goes outside of U.S. territory, then technically it's not CBR. It doesn't have to meet CBRS requirements. It has to meet whatever territory it's in. So yeah, unless I would think cruise ships in particular would be very tough to deploy CBRS given the requirements for precise location, because again, they're out there in the ocean where incumbents could be with U.S. Navy carriers. And if they're moving, they would have to check in and update that GPS location all the time. So I guess if you're talking like, if it's always real-time connected and updating frequently, potentially you could do it. But I don't know. Yeah.
Is the SAS global or US based?
The question is SAS global or US based? It's US based. CBRS is a US specific
So if I'm sailing around,
technology.
if I'm sailing around the Caribbean on a cruise ship,
Yeah.
like I'm going to report GPS coordinates to the rest of the US, and SAS is not going to know what to do with it necessarily.
Yeah, I don't see that being a defined use case for CBRS, at least at this point.
Do you think any other countries are still going?
Other countries, they'll jump on board with shared spectrum in some fashion. It's to be determined whether or not they match the CBRS regulations and requirements, or if they go their own way and just say we're going to do shared spectrum in our own way. Like the ones out there in Germany and the UK have already kind of done their own thing. They have shared spectrum, but it's different protocols, different requirements that they have to meet. So CBRS, think of it as a very unique use of the spectrum for the US. Shared spectrum will have potentially other requirements. So what you're going to end up having for private LTE solutions is, if I'm in the US, which spectrum bands am I using and what are those requirements? I'll have different software and algorithms maybe in the same system if I register it in a different country with different requirements. Just like you do today with Wi-Fi, you have to put in a country code or something like that. You may have to do for an installation of which country am I deployed in and what are the requirements I need to meet. But that's, this is future looking. This is all just CBRS based in the US right now. But I think in the next 12 to 18 months, we're going to start to see a lot of those other countries define their requirements, and we're going to start to see products integrate with those requirements and start to implement them. So a very valid question, but probably just not there yet.
So you think like the actual product, radio product, would probably be similar or the same with different hardware switches or something?
So the question is, will the radio, the product be the same product, just have different capabilities depending on where it's deployed? I can't forecast. I would imagine so in order to, serve the most amount of, use cases in a given product. But it's really to be determined on what those other countries' requirements are and whether or not that's feasible to do within the same product set or not. Once they get defined, then we'll know. So, let's say you take a small cell, a CBSD today in the US, it doesn't have to do any environmental sensing. That's all taken care of by the SAS. If another country comes out and says, no, every radio must do it, well, then the radios for the US probably won't meet the requirements for another country. You'd be looking at a different product. But if it's close enough that the products can overlap and still meet both use cases or multiple use cases, then I would think that would happen. Okay, so we've deployed our network. Then you get to the survey solution. We used IBWave as an example for predictive design. They also have a solution for CBRS surveying. They integrate with a lot of third-party tools because when you get into LTE, their tools integrate and survey for a lot of different 3GPP bands, licensed as well as CBRS. So in order to scan for those bands, their solutions typically require third-party tools in order to do the scanning all the different LTE bands, potentially worldwide. And they can also, with IBWave Mobile, pair it to Android devices and smartphones that support those bands and get the scanning data off of smartphones. On the right-hand side, I don't know if you saw Jamel on Twitter. He tweeted out, hey, what's this device I brought with me to WLPC? Any guesses? That was a PCTEL scanner that scans all of the LTE bands. So it's a dedicated scanner that you could buy if you don't want to pair smartphones with a tablet to do scanning. And that's what we use to actually scan the conference center. So there's Jamel. He's using his device, and that is what the walk test. So in cellular terminology, instead of an RF site survey, if you hear walk test, that's kind of what they mean. Is they're walking around, they're doing live measurements of what their coverage, SINR is, and actually gathering RF performance criteria. So there's a question on if there's a difference in received sensitivity based on the individual device and its manufacturing, right? I would imagine so. I don't know the answer offhand. I think, sensitivity is, they conform to more rigorous standard or testing than Wi-Fi does. So I think it's probably variable to a degree, but not to the degree that it is in Wi-Fi chipsets. Because remember, LTE chipsets are more expensive component-wise as well. They are a little bit higher quality, so they cost more. It's difference in market, right? Wi-Fi is very cheap componentry for the consumer market. Not very cheap, relative to other componentry. It hits a cheaper price point to hit mass market consumer, right? LTE has been a little bit higher price point, a little bit different componentry. So I would expect there to be some variance, but not as huge. Oh, with the SINR to data rate mapping? No, that's standard. If you hit this SINR, you need to hit this data rate or a very tightly controlled range of data rates. So there's less fluctuation, yeah. Yeah, I mean, I would say you can look at RSRP from a CBRS perspective. Do most of your planning off of SINR though. SINR is where the rubber meets the road in LTE. You don't really need to care about the RSRP as long as you're hitting a given SINR.
Like right now for Wi-Fi, we have to plan for LCMI. Is that still something that we have to think about for CBRS?
Can you repeat that one more time?
For Wi-Fi, we have to design around the least capable, most important
Oh.
device because a lot of the Wi-Fi.
I didn't understand that acronym first time.
Do we have to do the same thing for CBRS?
So the question is, do you have to design for the least capable device in a CBRS network? I would say no at this point. I would say you can pretty much assume most of them are a pretty tightly controlled performance profile. And that, if you're planning for this smartphone, it's going to be the same as the other one. If you're planning for a router gateway type of device or a bridge type of device, they're going to have higher gain antennas as well. So I think you'd be fine. There's just not the variance there is from my perspective. I'd be happy to be corrected though. So ask that question again tomorrow when our CTO is in and see if you get a different answer. I think he'll tell you that, that is just not a thing in cellular. They test, this carrier specifically tests for those performance profiles, so they don't have to have that variance. SIM models, I'm gonna just breeze through these. There's a whole, you just gotta get familiar with SIMs and how to provision SIMs. There's a lot of, the ecosystem right now from a CBRS perspective is actually fairly robust. It's grown quite a bit in the last 9 months or so. So smartphone platforms, you're looking at, I think I have them on here. Nope, next one. Smartphone platforms, you're looking at the iPhone 11, you're looking at the Google Pixel 3 and 4, Samsung S10, Note 10, S20. There's a lot of cradle point devices and routers, Sierra wireless devices, a lot of Ethernet bridges from like Multitech, a lot of point solutions for like video security like from Lanner, BEC. There's a lot of devices out there. It's a matter of mapping your use case to a device and mapping that also with potentially a customer's device lifecycle refresh. If they have devices that are not CBRS capable today, but they have a use case, do I want to buy an add-on device to bridge that, or do I want to wait for their device refresh cycle to get them into that ecosystem? And again, that's going to be a planning exercise of maybe you tackle a subset of devices today, and over time you're going to grow their private LTE deployment as more devices get lifecycled or deployed.
What about eSIM options for Celona?
eSIM is on our roadmap specifically as a manufacturer, fully supported. I mean, everything just carries over from LTE. So if you're looking at just generically in CBRS, it can be a physical SIM, it can be an eSIM, it can be an iSIM, which is a system on a chip with a processor. Any of those are all supported, it's just the SIM protocol has to be followed.
Who generates the SIM then? The enterprise or?
So the question is, who generates the SIM and manages them? An enterprise would at this point, because you're fully under your control as a network, as an enterprise. So within Celona, we developed our own subscriber management system where you can provision and deploy SIMs. Today for us, that's physical SIMs. On our roadmap, and later this year is eSIM capability for deploying it onto an eSIM on a device. Which is still hardware based on the device. It's just you have it on the motherboard on the device rather than a removable. So yeah, physical SIM, eSIM, or iSIM. Today, we just happen to be physical SIM through our product development. Over the within this year, we'll have eSIM capability.
Does that mean the device that has a SIM for CBRS?
So the question is, does that device?
To a public SIM?
So the question is, does the device have a SIM for CBRS? The answer is yes. You have to have a SIM that is the credential to get on the network you want to get on. So just like you have credentials for a Wi-Fi network today, the SIM that you provision on the device has to have credentials for your enterprise network, which means your subscriber management system, whether that's bundled in with the network infrastructure or whether it's a third-party add-on system, which is fully out there and capable, you can go buy one off the shelf. it has to be your SIM that you've provisioned and your system can authenticate. The second question, integration and roaming with carrier networks, is a little bit longer term. The CBRS Alliance is looking into neutral host options. The problem is, from a standards perspective, it is fully capable. It's just, integrating with a carrier's packet core and network for roaming. That's more of a business partnership for federated authentication, very similar to Passpoint and Wi-Fi. It's business relationship oriented, not technology oriented. So I'd say right now there's no solution on the market. There's no integration capability today because the carriers aren't really actively invested in that. There's a lot of momentum in the CBRS Alliance to try to bring those parties together to enable that functionality. So look for the CBRS Alliance to drive that from a business market perspective. But the technology and all the protocols and capabilities are there.
So the iPhones you have back there, you can plug and walk outside.
Yeah. So right now, what we're going to show today or tomorrow for a demo and you can play with is it's a private LTE SIM only. It will not connect to Verizon, AT&T, T-Mobile, anything like that. There's no partnership at this stage of the game right now to federate that authentication. What does a SIM contain? Real quick, it contains asymmetric cryptography keys. It does not contain identity, it's just the keys. So when you're provisioning a SIM, you're mainly provisioning PKI. You're provisioning keys. A SIM is really just an encrypted secure container for file structure and holds multiple files. Those files can include some things for LTE like your home PLMN, which is primary land mobile network, which is essentially, hey, which operator? Each operator has an ID that contains the country code and the operator's unique ID. Which one is mine that I should connect to? Which ones are equivalent to mine? So if I go out of country and I need to get service, which ones should I look for and connect to? And then which ones are roaming PLMNs, which potentially are my last resort? Because typically the operator then needs to pay a back-end charge to get roaming data on a different carrier's network. It also includes the device's identity, or the IMSI, which uniquely identifies that SIM and that device to authenticate to the network. And then it has a whole bunch of other files for like your phone book and service dialing for operator service numbers, SMS, parameters, all sorts of things. Question?
Is it possible?
Yeah, Sean, and then I'll get you, Heather.
Is it possible, let's say, hey, I got my CBRS set up over here, and then let's say a mile down the road, I got a bunny office, completely different installations, but I want to roam onto their network also. Is there a way to share that information?
So the question is, if I have two private LTE networks, could I enable roaming between them? Yes, you would be programming your SIMs and your subscriber management system with an equivalent PLMN or a roaming PLM with the other network. So you could have federation. Let's say, one of the interesting use cases is like equivalent to EduRoam in higher ed. You could do very similar with equivalent PLMNs and roaming PLMNs, program those into your SIMs, and you can actually update SIMs with an update profile. I don't know if you've ever gotten one on a carrier network. Hey, update your SIM profile. Your operator's pushing a new profile down. You can do that dynamically so that you could deploy them today. Hey, they came online. We want to push out their ID so they can roam onto them. I could push that out and update my clients to do that. Oh, hold on. I want to get to Heather first. Heather?
I was just going to point out that this scale information listed by having the CPI programming to do it indicates that only the user device is allowed to roam. So there's no way to put this information into the base station. So the CBRS station cannot roam, so it cannot push.
Yeah, so the question was, this is UE or user endpoint specific, not infrastructure or CBSD, right? There's no concept of roaming for infrastructure eNode Bs. As in what? Yeah, I mean, this is purely a client roaming situation, yeah. Mike? Oh, sorry, Jim. So the question is roaming PLM is authenticated. Yeah, so there's a roaming relationship. There is an actual tunnel between one packet core, called a serving gateway, back to the originating home PLMN operator's packet core. And yeah, everything gets tunneled back. We went over types of SIMs, just form factors. There's removable SIM, eSIM, which is embedded. It's on the motherboard. And then, so the thing is, the form factors come into play when you think about if I do want a device that needs dual SIM capability to be on both a private LTE and a carrier's network, what are my options? The big thing to note is that eSIM, you can only deploy one to a device because there's one eSIM module on the motherboard of a device. You can only deploy one profile to a device. So you cannot deploy multiple eSIMs to a device. So if you're doing dual SIM, you can do 2 physical SIMs if the device supports it, 1 physical, 1 eSIM, or 1 physical, 1 iSIM, for instance. So your dual SIM options are typically 1 physical, 1 eSIM, or 2 physical. And then you'd set one as your primary, so whichever one needs to be your primary, just think about which one you want to be physical versus an eSIM. So for right now, like we've done a lot of testing on our stuff with, since we only support physical SIMs right now, moving the carrier to an eSIM, putting in a physical private LTE SIM, and then you can get dual SIM capability, so you don't necessarily roam between the private LTE network to the operator. You're not federating authentication. You just have authentication to both, and then the handset or the device itself has logic on which one it wants to connect to based on its signal quality. And it can fall back. And it can have a primary for data and a fallback for data. So you don't necessarily need carrier roaming if you do a dual SIM type of setup. And so there's a couple of use cases. Travel, international, you might want a secondary SIM. Multiple subscriptions, which is the private and carrier within the same location. And then you might want, constant coverage if you're going in rural areas. You might want, hey, they have a coverage gap on one carrier. I want a secondary carrier for that area that covers it. Configuring dual SIM on a smartphone. You can do it on iPhone. You can do it on Android. Just a matter of popping in the SIM, going into the settings, and selecting, which one's going to be your primary and secondary for data. And it's as simple as that. We're working actively with Apple and Google and others to work on their selection algorithm of which one they connect to and when, because right now you will have a break in service. It's very interesting if you're going from a secondary SIM operator into your primary, that transition happens very quickly. Because when it sees the primary, it wants to switch to its primary right away. When you're going the reverse, primary to secondary, it tries to hold on to that primary for as long as it can. So sometimes you'll get a break before it finally times out and triggers to go to a secondary, because it wants to be more conservative and stick to the primary. So we're talking order of magnitude of maybe not noticeable going from secondary to primary operator. Going from primary to secondary, you're probably looking at, right now, tens of seconds for it to figure that out and switch. So it's not horrible, but it's definitely not seamless. That's all the operating system manufacturers through the handsets and the devices, yep. It's their algorithm to select which network to connect to. Yes, it will change over time. They're actively working at improving those algorithms. There's a list. When you get the slide deck, you can look through here on what devices are capable of CBRS today. This is more reference material, so there's tablets and smartphones out there, more smartphones that I didn't mention, like LG has one, OnePlus has a couple. There's dedicated embedded devices for specific use cases, like bridges, cradle point routers, Sierra Wireless bridges and modems. You get into more industrial manufacturing type use cases, connected vehicle type use cases where these become important. Video recording solutions for security purposes.